All right, so this is the bonding unit, continuing the bonding unit. We're going to talk about Lewis structures, talk about resonance structures, formal charges, expanded octet, and molecular geometry. Maybe. All right, so in Lewis structures, we represent molecules using element symbols to represent the bonds to represent the atoms in the bond or in the molecule. We represent the shared pair of electrons as either a line, or you can draw that shared pair as a pair as well. When atoms have unshared pairs, it is important to draw them and to draw all of them. Remember that the total number of electrons in a structure can only be the valence electrons or electrons that you have added or subtracted to make a charge on them. Right. So one way to draw Lewis structures is to add up all of the valence electrons so you know how many to put in the structure. If it is an anion, meaning it has a negative charge, you're going to add one electron for each negative charge. If it's a cation, a positively charged ion, you're going to subtract one electron for each positive charge. And you want to bear in mind that that is the total number of electrons that you can have in that structure. I look at these structures perhaps a little differently, but some rules to keep in mind. One, your least electronegative atom is going to be in the center, all right? And we typically think about an atom in the center with things coming off of it or things being bonded to that central atom. And the one in the center is the one that's least electronegative, which is usually also the one that's going to make the most bonds. Right? You're told it's a molecule, so the first thing that you should do is you should make it a molecule by bonding all of the atoms. If you look at phosphorus, I do it a little different than they do. If you look at phosphorus, phosphorus has 5 valence electrons. I tend to draw those 5 valence electrons on the center atom, or however many electrons that center one has. Each chlorine has 7. Right, so I would attach one chlorine here, one chlorine here, again drawing the 2 electrons in between the 2 symbols representing the bond between them. Then I would make sure that my number of valence electrons are all correct and I don't have any more than 26, and that would be my structure. I tend to use different symbols to keep track of valence electrons. You do not have to, but again, you have to make sure that you haven't added or subtracted any electrons. Keeping in with this second procedure, okay, connect them all with a bond, fill in the octets of the atoms on the outside, then fill in the octet of the central atom. All right, all the while keeping track of the number of electrons that you've used. Well, we're going to draw something like hydrogen cyanide. I have hydrogen with 1, carbon with 4, and nitrogen with 5. The least electronegative, with the exception of hydrogen, is this carbon. I'm told that there is a bond, so I'm going to put these together with one bond between them. And in looking at this, you can see that I have 2 empty spaces here in the carbon and 2 empty spaces here on the nitrogen. If we were to move these electrons in to form a bond, would that make everything stable? Because I obviously wasn't stable quite yet. Hydrogen has 2, carbon has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen 1, 2, 3, 4, 5, 6, 7, 8. So everything is stable. And that's kind of how I do it. Again, following their Prentice-Halls. Make the bonds between them, add electrons on the outside, If you run out of electrons before the central atom has an octet, then form multiple bonds until it does. All right, so it's very similar. Now let's talk about formal charges. If we look at the Lewis structures for carbon dioxide that were drawn here, we would see that these do obey the octet rule. And I do have the correct number of valence electrons. This is typically the Lewis structure that you will see for carbon dioxide, and that should be the one. All right, but how do you decide between this structure or this structure? Because they are both valid Lewis structures with stable octets. What we're going to do is assign formal charges. Okay, please bear in mind, these are not actual charges. All right, these are not actual charges. They're just formal charges. They're kind of a bookkeeping thing to make sure that Lewis structures are valid, more valid. Sometimes they fall apart, but we'll look at that in a minute. All right. What we're going to do is we're going to take the number of valence electrons for each element. Oxygen has 6, carbon has 4, oxygen has 6. And then we're going to subtract the number of electrons assigned to the atom. What I tend to do is draw a circle around the atom, and I'm going to count how many are its closest neighbors, meaning in this bond between oxygen and carbon, one of the electrons is assigned to the oxygen, one is assigned to the carbon. So in this oxygen, I have 1, 2, 3, 4, 5, 6. 6 minus 6 gives me a formal charge of 0. And sometimes you'll see me write them on here. This carbon, same way, has 0. This oxygen has 0. Looking over here, here is my oxygen. I have 1, 2, 3, 4, 5, 6, 7. So I have 6 as the valence electrons. Minus 7 assigned, I get a minus 1. Oops. I don't know how I did that. Okay, so over here, I get a minus 1. Carbon is still at 0, and oxygen is at plus 1. How do we use these formal charges to decide on what is the most valid or the best Lewis structure? The best Lewis structure is the one that has the fewest charges overall. Okay, if you have to have charges, you're going to put it, it's the Lewis structure is the best Lewis structure that puts the negative charge on the most electronegative atom. So if you look, if we were evaluating these Lewis structures based on formal charges, this -2 is on this nitrogen. Oxygen is more electronegative and it has a +1. But even before we get that, this has a -2 and a +1. This has a -1 and 2 zeros. This one's out because it has too many charges. Now these two are very similar, but I've got a -1 on the nitrogen. Here I've got -1 on the oxygen. What element is more electronegative? The oxygen is, so this one is the best Lewis structure. Okay. Let's talk about resonance. Okay, so in resonance, we have a Lewis structure drawn for ozone. These, and we would expect to see a single bond on one side and a double bond on the other. So these lengths should be different. This double bond should be shorter. This single bond should be longer and weaker. What we actually observe experimentally is that ozone has the same bond between the oxygens. It's the same length, and the outer charge on each is about a -0.5. So really what happens is that one Lewis structure doesn't really show what is in the molecule. So those bonds actually in ozone are more like a 1.5 bond. So if we were to draw the Lewis structure, this one, and then just put the double bond on the other side, in reality, the ozone molecule is a mixture of these two. This second bond actually gets blended across the molecule. Okay, we draw that with Lewis structures just by changing the location of that double bond to all the places that it can be. Again, it is a mixing of that one and that double bond, and you actually do call the bond order 1.5. So here's another example of a Lewis structure that would have resonance, and what you look for is if there's a double bond that could also be somewhere else in the molecule. And again, that pair of electrons in that double bond is kind of mushed or blended across that entire, that entire part of the molecule between both of those oxygens and that carbon. They are said to be delocalized electrons. One very important compound, benzene, has two resonance structures. And you can see in the benzene molecule that I have alternating single and double bonds. In reality, what I have is those bonds being shared across pretty much that entire molecule. So all of these bonds, I neither have a double or a single. I really have 1.5 bonds. You can draw benzene like these two structures, or you can draw benzene like this structure with a circle in the middle representing the resonance, the sharing of those electrons in that double bond. And that signifies those delocalized electrons in the ring. There are some exceptions to the octet rule, and you need to be familiar with these. There are going to be ions or molecules that have an odd number of electrons. If I have an odd number of electrons, I can't have every element or every atom with an octet in its valence shell. There are ions and molecules that are stable with less than an octet, and there are ions and molecules with more than 8 valence electrons. The ones that you're familiar with already is hydrogen. But we're going to add beryllium and boron. Okay, beryllium is stable with 2 bonds in its valence level, or 4 electrons. Boron is 3 bonds, or 6 electrons. And we'll talk about this expanded octet in a moment. Odd number of electrons. Nitrogen monoxide. We know that this is a compound, right? They are fairly rare. They're usually unstable and reactive, but they do exist. All right, so a nitrogen monoxide could be drawn this way or could be drawn this way. I'll leave you to decide using formal charges which one you would make an argument for. Okay, and then boron, F3. What this is showing is if I make that double bond, if you look at the formal charges, it has boron having a -1 charge. That's not likely because fluorine is the most electronegative atom or element, and it's typically not going to do that. So the Lewis structure that you should draw is the most important Lewis structure, and that's the one that would have boron with just 3 bonds, 6 electrons in its Lewis structure. These may occur, but we're pretty much going to say no. The most important one to draw is this, boron trifluoride. So, rule of thumb. If filling the octet of a central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, do not fill the octet of the central atom. The two examples again are beryllium and boron. Hydrogen. I guess it's 3. All right, so more than 8 electrons. We do know that phosphorus pentachloride exists, and it exists only if phosphorus has 10 electrons around it. You may be asking yourself, wait a minute, how can that be? If we have an atom that's on the 3rd row or below of the periodic table, then we have a d orbital that these atoms can use to participate in bonding, right? I think I want before we move on, how would you go about drawing the Lewis structure for something with an expanded octet? Let's go back down here and look at phosphorus. Again, I would draw phosphorus like this. I know that it's PCl5, it is a molecule. I'm going to put 3 chlorines here, which I think you would agree upon. Now I have 2 more. You see how I have this pair of electrons? You can envision this expanding of the octet of taking this pair and splitting it between the 2 remaining chlorine atoms. It gets a little hectic to draw them, all right, but then this is really how you would draw it. This atom, or I'm sorry, this molecule, oh, I thought I could change colors. Now has 1, 2, 3, 4, 5 electron domains. Okay, let's take a look at the phosphate ion. We can draw a Lewis structure for the phosphate ion that has 8 electrons around the central atom and features a negative charge on its more electronegative oxygens on the outside. However, if we make a double bond between the phosphorus and the oxygen, I can lessen the charges. And remember, that's the first thing that we want to do is the less charges, the less formal charges on a Lewis structure. Would I expect you to come up with this on your own? Actually, no. But now that you've seen it for phosphate, you should remember phosphate. All right, so the lesson here is when the central atom is on the 3rd row or below and expanding its octet eliminates some formal charges, you should do so. Okay. It's probably long enough. Let's make a different screencast.